Hey everyone, in this video, let's take a look at question 153, find minimum in rotated sorted array on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we are given an array of length n which is sorted initially in ascending order, but the array has also been rotated between 1 and n times. For example, if the array was something like 0, 1, 2, 3, 1, 2, 4, 5, 6, 7, then if we rotate it 4 times, it becomes 4, 5, 6, 7, 0, 1, 2. You could think of rotating as basically taking this last element here, bringing it to the front. Then you take this one, and then you bring it to the front again, etc. So this one, if you take a look at this, it's actually been rotated 7 times. If you repeat this 7 times, you actually arrive at the same array again. What we essentially want to do in this question is we want to find the minimum element in log of n time. Now we can make some notes here. First of all, the array has to be sorted initially. So that's one guarantee. Another guarantee is that the array always contains unique elements, so we don't have to worry about duplicates. Okay, so we have those two guarantees. But what else do we know? Well, we know a way to do this, right? Like if it was not log n time, if it was just O of n time, then we could just go through it and figure out what the minimum is that way. But here we have a log n time. So often when you see log n, you might automatically think of like binary search, right? Especially when you're talking about arrays. But how can you really do binary search here? Because it's not sorted, right? Like this is not sorted. So how can we go about doing binary search? Well, if you go ahead and you draw some images and you draw some just sample arrays and you try to draw like the line graph that follows them, it actually becomes clear in a way in which we can actually use binary search to solve the problem. Because binary search, although it often requires a sorted array, it doesn't necessarily need it. If you know like the underlying mechanism to which why this array is not sorted anymore, if you know some more information, then you can actually use binary search to arrive at your solution. Let's take a look at how that might happen. And first thing I'll do is I'll actually just take a look at these examples that I have here. Let me do that. And so we already know kind of out of the output and why we can just see the minimum element directly. But kind of take a notice of this, like what's happening here. In the nums, if you take a notice of like what's happening and you draw like a line graph, then notice how like from 4 to 5, we're increasing. And we often like keep increasing until we arrive at the 0, in which case we decrease, and then we increase and we increase, right? Over here, it's kind of like very similar. So we have increase, 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 decrease, and then increase. Same thing here. Okay, so in this case, actually, we're entirely increasing, which means it's completely sorted. Here, we're increasing, and then we decrease once, and then we increase again. Here we increase, and we decrease once, and we increase again. So let's take a look at what this kind of means. So if we have like a sorted array, which we have over here, the entire thing is going to be increasing. So that's what this green means. Entire thing is going to be increasing. Maybe if we have like a pivoted array, like a rotated array, right? We're going to be maybe increasing, and then we'll have one decrease measure, and then we will increase. Now, notice something here. Notice that this peak that we have here, will never be reached by the right-hand side, right? The right-hand side, it will never go through the peak here. It can't do that. And I'll explain why in just a moment, but let me take a look at the second and the third example over here. But again, you can see we have like the same set of format, right? So we have increase, we'll have one decrease, and then we'll have an increase again. And notice that again, this right-hand side, it cannot go over this. It cannot go over this. If it does go over this, then what does it mean? Well, then it means that the entire thing is increasing. It means that the entire thing is increasing. Why? Well, let's basically think about this, right? Like the array is initially given to us in a sorted format, right? Like the array is initially given to us something like this. So we know that initially we're going to have something like this, right? And now notice that the moment we move an element to the end or to the start, the moment we perform one like rotation, we'll arrive at something like this, right? And the array is kind of still sorted. This part is still sorted, right? So now note here, what do we have? Well, we have initially have something at the very top, right? We have something at the very top, and then we go down, and then we increase. But notice that because the array was initially sorted and we rotated, this first item here can never be less than this item here unless we're stuck with the original array, unless we're stuck with something like this. Because if you think about it, like every time we rotate this array, we do something like, maybe let's do a couple of rotations. So 5, 6, 7, 8, 9, and then 1, 2, 3, right? Every single time, this element here, this first element, will always be greater than this last element here. simply because the array was initially sorted, and then we performed the rotation. The only time that we'll have that the leftmost element is greater than the rightmost element is if the array is basically at its original form again. So that's something we can note from here. Okay, so we noted that. Now, what else can we do? Now, notice here that this spot that I've marked, right? Like the spot that I've marked, this is essentially like the midpoint. This is the midpoint in the binary search. It would basically be equal like to the left-hand side here plus the right-hand side here divided by 2. And this is an I and a D. It basically means like increasing, decreasing, increasing. Okay, so we have that information here. So we made a couple of observations, right? We noted that left-hand side is always greater than rightmost side unless array is already sorted. So we already made this conclusion over here. Now, what exactly are we trying to do in this problem? Well, we're trying to find the minimum element, right? And if you think about it, this like thing that we have here, like this dip that we have here, it can only occur once in the array, right? Because the array is already sorted. We cannot have a scenario where we have something like this. Like we can't have like 2 dips over here. That's impossible. The only thing we can have is a single dip because the array has already been sorted. Just go ahead and try with a simple example that's already been sorted. So try with something like this. Go ahead, move the 9, move the 8, move the 7, and notice how we always just have 1 dip. And so that dip that we have has to be the minimum element, right? It has to be the minimum element. This is actually kind of badly drawn here because this shouldn't like start off at 0. This should really like start off at the 7. Like it should actually start off at the top. But basically, if you think about this one, right? Like if you think about something like 7 and then something like this, we have something which follows like this scenario. And notice that the right-hand side can never be greater than the left-hand side. Okay, so now we know another thing. So we basically know that our answer of minimum element has to be the dip, right? It has to be the dip. And we also know dip can occur only once. So we know these 3 things. Okay, so we have all of this information. Now, how might we go about doing binary search on this, right? Like in binary search, what do we need? So I'm going to go ahead and let's go ahead and consider these 2 examples here, right? Consider these 2 examples. And what I will do is I'll just zoom in a little, right? I will zoom in and let me consider this one at the bottom over here. Okay, so what do we start off with? Well, our left pointer is over here, our right pointer, and maybe I can actually write this because, okay, so left pointer is here, right pointer is here, the mid pointer will be over here, okay? So what can we know? Well, take a look at this graph over here. If we are like at the mid pointer, right? Like we might be over here, we might be over here, we don't know where we are. But essentially, notice that like we have the scenario where like all of the items will be increasing except for the dip, right? So basically, from this scenario here, we know that on the right-hand side, like overall, we must be increasing. Sure, there might be a dip, and actually in this case, it turns out there is a dip, but overall, we're going to be increasing. And I'm actually going to zoom out. Okay, so overall, we will be increasing. What can we like actually understand from this? Well, if you think about this, we have a 9 over here, right? And we have a 4 over here. What does that mean? Well, if we have a 9, and then we have a 4 later on, then we know, right? Like we know that there must have been a dip, right? Because otherwise, we would have just continued increasing. 9, 10, 11, 12, etc. We would have just continued increasing. We already argued that we can only have 1 dip inside of the entire array. And if we have that dip, then we know that there's a minimum there. The only way that we have 9 in the middle point and then 4 in the end is if there is a dip on this like side of the graph. So we already know basically that there has to be a dip somewhere here. And we can actually do better than that. There has to be a dip actually somewhere here. We can ignore the midpoint because we know that the midpoint is essentially greater than the 4 here, right? So it cannot be the answer. So that's one scenario here, that this has to contain the value. And we can actually see that here, the midpoint is greater than the right-hand side and the dip is actually over here. So 1 is the value. So that's something we can also know. Now, what if in this case, the midpoint is over here and the right-hand side is actually greater? It's greater than the midpoint. Well, what do we know? Well, we know that the values, they have to be increasing, right? They have to be increasing. And if they are increasing, so take a look at these values here. If the values are increasing. So we have something like 9 and then 1 and then 4. Basically, they can never be, the value on the right-hand side can never be greater than the value in the minimum unless it was a strict increase, right? Unless it was a strict increase. What do I mean by this? We cannot have a scenario where we have like a 2 over here. We have a 2. If 2 we notice is over here and 6 we notice is over here, we cannot have a scenario where we have something like this. We can't have a dip and then an increase, because we already argued that if we have that, like the dip can never go above the value, right? So the dip here, we can never go above this line over here. We can never go above this line over here unless it's like already like that from the start. So in this case, right, like if we are at the midpoint here and we notice that the right hand side is actually greater than the midpoint, and we know that we often always just increase unless we're at the dip, then we know that actually the dip cannot lie on this hand side. It cannot lie actually right over here, right? It cannot lie here. Well, first of all, we know it can't be at the, we know it like, it can possibly be at the midpoint because mid is less than like this value here. So we know that much, but we also know that the dip cannot be here because first of all, like the value is greater than the midpoint here. And if there was some sort of dip, it would have never crossed this 2 value over here. It would have never crossed this 2 value over here. So if we had a 2 over here, we might have had like something like this, right? But the dip can never have crossed the 2 value over here. So we would have a scenario, something like this, right? You would have this scenario here. So given that we have that 2 pieces of information, essentially we know that the minimum must be on the left-hand side. The dip must be on the left-hand side. And it's possible that 2 can actually be the minimum, right? Like, because if you think about it, let's say in this case, if we considered 1 as our midpoint here, well then 1 is definitely less than 6, but you can notice that 1 is actually part of the minimum here. So we know that this much is not valid, but it's still possible that this is valid. So given that we have this information, now we can actually use binary search. So let's take a look at how we can go about doing that. Well, with binary search, we often always use the same formula. So I'll set my left pointer to 0, right pointer as length of nums minus 1, and then I want to loop, right? I want to do while L is less than R. Now, in other problems, you might do less than or equal to, but if you do this, then you should be expecting to actually return from this function here. If we don't want to return from this function and we just want to return like when L and R are equal to the same value and we have arrived at our minimum, then we use less than R. If you use less than or equal to, then you're expected to actually return from inside of the binary search. So that's just something to keep in mind. So if we have this, let's go ahead and find our minimum, which is L plus R divided by 2. And then we can check. So we can check if nums at mid, if this value, so what did we argue here? If nums at mid, if we are at this value here, 2, if this is actually less than the one at here, like the value over here, if this is that case, well, actually, let's maybe consider this case here, just our kind of like happy case. So basically, if the value we have at the mid here, if it's greater than the rightmost value, then we know that the dip must have occurred on the right-hand side, right? We know that the dip must have occurred on the right-hand side. So if nums at mid is greater than nums at R, then the dip must have occurred on the right-hand side. So we can actually just go ahead and increase our left pointer to equal mid plus 1. Why mid plus 1? Because we know that mid cannot be an answer because mid is definitely greater than this element here. So it has to be mid plus 1. We're essentially going to be moving this mid pointer, or this left pointer essentially, to, and let me make this bigger, we're going to be moving it right over here. So we're going to be doing that. Otherwise we can move our right pointer to mid. That's the other case. That's this case over here. Our midpoint is over here at this 2 here. And we can see that if it is greater, if the right-hand side is greater, then we know that we've had a strict increase. So the decrease, the dip, must be on the left-hand side. And we know it could possibly like be that 2 is the answer, right? Like just consider maybe like this scenario, if this is the mid somehow, then like mid can definitely be the answer here. So we will go ahead and we will consider this value over here, 78912. So we can do that. So we can just do right is equal to mid. And at the very end, we can actually just note that left and right would be equal. So we can actually just return nums at L. And so that will be our answer. So now let's go ahead and run our test case. Now we can go ahead and submit. And we should see that this gives the correct answer. So in this scenario, our time is log of n, and our space is actually just O of 1. I hope this video helped.